winter break, got a chance to rest and recharge. Yeah, for the second half of the school year. So yeah, I hope you guys had a good couple weeks off. But so today we are going to start our next chapter, chapter 5, and it's going to be all about projectile motion. Okay? So it's going to be kind of combining our forces that we looked at last chapter and our kinematic equations that we looked at in chapter 3. So when we're talking about a projectile, we are talking about an object upon which gravity is the only force acting. So when we're talking about something in projectile motion, our only force acting on that object is going to be gravity. Okay. So that means we're probably most likely in the air. And we know gravity always points straight down. So the only force acting on our object here is that force of gravity pointing downward. And remember, no matter where that object is in its motion, okay, so even if that ball or object is moving upward, it's moving to the side, whenever something's in the air, the only force acting on the object is gravity. And so it continues its upward motion because of inertia. Remember, we want to maintain our state of motion unless we're acted on by an unbalanced force. So even if we're moving upwards, it's just that inertia that's carrying us up, and we have that force of gravity pointing downwards. Okay, so since we only have this vertical force, we're going to kind of look at our x and y variables independently. You're standing on a cliff and you throw a ball straight out. Okay, you throw a ball straight out and then it moves until it hits the ground. Okay. If we look at our x and y direction here, okay, initially we only have this horizontal component of our velocity because our ball is being thrown horizontally at first. Okay, so we only have that horizontal component. However, now as our ball starts to move, now we're also going to have a vertical component. Okay. So since we have no forces acting in the horizontal direction, we're not going to have any acceleration. Okay, so our velocity in the horizontal direction always remains the same because we have no horizontal forces acting on that ball, causing it to change speed. Okay, so that's going to be a big idea here. So we have no forces in the horizontal direction. So that means there's no force to change that ball's motion. So that means we're not going to have any acceleration in the x direction. So horizontally, we're going to have a constant velocity. Okay. So no matter where we are in our ball's motion, we're always going to have that same horizontal velocity. Okay. However, if we look vertically, now we have that force of gravity acting in that vertical direction. So that velocity in the y, or in the vertical direction, is going to become increasingly negative, or increasingly directed in the downwards direction. Okay, so as we go on, that vertical or that y velocity is going to increase. Okay? So since we have that force acting in the vertical direction, we are going to have something causing our motion to change, and we're going to accelerate. And since gravity points downwards, we're going to accelerate downwards. So velocity in the y direction becomes more negative. And we should remember, whenever something is in the air, okay, whenever something's in free fall or is a projectile, we already know what our acceleration is going to be. Okay? So we should remember that special number, that negative 9.8 meters per second squared. So that means with each second, our velocity is becoming more negative at a rate of negative 9.8 meters per second. Okay, so that velocity is changing in that vertical direction because we have that force of gravity acting there. And this is where then our kinematic equations are going to come into play. So remember back from chapter 3, those kinematic equations relate our different variables of motion, okay? And since we're looking at our x and y direction independently, we're going to kind of look at different equations we're going to use in each direction. Use when looking at projectiles or an object in the air is going to be our equation that our displacement, or delta x, is equal to our initial velocity times time plus 1/2 acceleration times squared. So this equation should look very familiar from chapter 3, and this is going to be the kinematic equation that plays a large part in our projectile motion. Okay, so we're then going to apply this then in our horizontal and vertical direction. So to make it a little bit easier, instead of just saying delta x there, because we're looking each direction, we're just going to say our displacement. Okay. So then if we're looking horizontally, okay, here we're looking at our change in our vertical position, or sorry, horizontal position, or x direction, okay? So we would take our initial velocity horizontally times time plus 1/2 acceleration times squared. Remember, in horizontally, we don't have any forces acting. So horizontally, our acceleration is just going to be 0. Okay, remember that horizontal velocity is not changing. So then if we want to describe how far we're traveling horizontally or in the x direction, all we're going to do is take our initial velocity in the horizontal direction, or how much is being directed in the x, times however long it's in the air, times that time. Okay? And remember, delta x, that is going to be our displacement, or more specifically, when we're looking horizontally, we're going to call that our range. Okay? And that is going to be the horizontal distance between wherever your ball was launched and where it lands. So if we look back at our previous example, this displacement right here, that would be considered our range or a delta x. Okay. So that's our main equation we're going to use in the horizontal. Our horizontal distance traveled can be equal to our initial velocity times time. Looking vertically, now we're talking about our displacement in the y direction. Okay, or how is that vertical position changing? And to find that, we're going to take our initial velocity that's directed vertically, our initial velocity in the y direction, times time, plus 1/2 a squared. Okay. So remember, looking in the vertical direction, we always say that force of gravity. So our acceleration is always going to be that negative 9.8 meters per second squared. Okay. When looking at our initial velocity y, we want to see how much of our velocity is directed vertically. Okay. So if we look at this initial example, we just threw our ball straight out. We just threw it horizontally. None of that initial velocity was directed vertically. We just threw it straight to the right. Okay. In cases like that, our initial y velocity is going to be 0. Okay, so if our object is thrown horizontally, okay, it's not thrown up or down whatsoever, that means our initial y velocity, or our initial velocity directed up or down, is be 0. Okay, so if you know you have a horizontal projectile, something that's just being thrown straight out, then your initial y velocity is just going to be 0 meters per second. And remember, that delta y, that's the change in your vertical position. Okay, so that would be the distance from where your ball starts vertically to the ground. Right here, oops, would be delta y then. We have Thelma and Louise, okay, and they're going to drive off, put them in their little car. Oops, I'm not an artist. A 100-meter high cliff. Okay, so they're starting off 100 meters above the ground at 12 meters per second. Okay, so they're just driving horizontally, and then they drive off that cliff at a rate of 12 meters per second. Okay, so let's kind of look and see what information we know before we get started. And remember, we're going to look at our horizontal and our vertical direction separately. Okay, so horizontally, we know that Thelma and Louise were traveling initially at a rate of 12 meters per second. since when you drive a car, you're just moving right or left, that is all going to be directed in the x or the horizontal direction. So our initial x velocity is going to be 12 meters per second. Okay. We don't know yet how far from the base of the cliff they land. So that's going to be all we know in the horizontal direction. Okay. So then looking vertically, here, we know whenever we're in the air of a projectile, our acceleration is negative 9.8 meters per second squared. Okay, so in that vertical direction, since we have gravity, we're always going to have an acceleration of negative 9.8. We also know that thermal leaves travel a vertical distance or have a vertical displacement of negative 100 meters because they're going to end 100 meters below where they started. Also, since this is a horizontal projectile, or they were initially just driving in the horizontal direction, none of that is directed vertically or in the y. Their initial y velocity is going to be 0 meters. Okay. So now let's look and see what we're trying to find out. Our first question is going to see how long does it take them to hit the ground. So we're going to want to find our time. If we go back and look at our equations, horizontally, we have the equation delta x for horizontal range is equal to initial velocity times time. Since we only know one variable looking at the x direction, we don't have enough information to use that equation just yet. So let's look at our equation in the vertical direction. Here we have our delta y, or vertical displacement, is equal to initial y velocity times time plus 1/2 at squared. If we look at this equation, we know that vertical displacement is negative 100. We know our initial y velocity is 0 because it's all directed horizontally. And we know our acceleration is negative 9. So looking at that equation, we only have one unknown. We're able to use that to solve for time. Okay, so we said our vertical displacement, our negative 100, equal to our 1/2 at squared. Okay. And when we solve that for time, we're going to find the Thelma and Louise are in the air then for 4.52 seconds. Okay, so we need more information looking at the y direction, so we wanted to start off looking vertically. Okay, and using that information, we were able to find that we're in the air for 4.52 seconds. Our second question is we want to see how from the edge of the cliff do they land. So here, we're trying to find our range, our delta x. So we're going to want to look at our horizontal equation. And here we have our range, or horizontal displacement, is equal to initial x velocity times time. Okay. So look at that one. We don't know our range still. That's what we're trying to find. However, we do know our initial horizontal velocity is at 12 meters per second. Now we also know that they're in the air for 4.52 seconds. Okay, so we found what that time was by looking in the y direction first. Okay, so it's always a good idea to start off with which direction you know more information in. And since we knew more vertical information, we started looking at that information first. Okay, so we're able to plug in the time that we solved for because we found that they're in the air for 4.52 seconds. And we want to see how far they travel horizontally in that time. And we should find that they travel 54.21 meters from the base of the cliff. Okay, the range here is going to be 54.21. Traveling 12 meters per second for each second. So if we take that 12 meters per second times how long they're traveling, that rate at that 4.52, that'll tell us how far they traveled. Okay. Whereas vertically, remember that velocity is changing by negative 9.8 each time. So while our horizontal velocity always remains at constant 12 meters per second, that vertical velocity is changing at a rate of negative 9.8 meters per second each second. Okay, fall off a 95 centimeter tall table. That means vertically, our ball is traveling distance of 95 centimeters. Okay. And also tells us that the ball then lands 30 centimeters away. So our ball is traveling a horizontal distance of 30 centimeters. Wow, I did not draw on that picture to scale. Oh well. So we want to see how fast was the ball initially moving as it rolled across our table. So when that ball rolled across the table and eventually rolled off the edge, how fast was it moving? Okay, so let's look at this one the same way that we looked at our last example, by looking at our two directions separately. So looking in the x or the horizontal direction, okay, here, we don't know our initial x velocity, okay? That's what we're trying to find. Trying to find how fast we're moving horizontally at the very beginning. But what we do know is that that ball travels a horizontal distance when it's in the air of 30 centimeters. We don't really care how far it rolled on the table because we're just looking at our ball when it was a projectile. Okay, so when it was in the air, what horizontal distance did that ball travel? And we know that's 30 centimeters, but remember, we always put it in meters. That's going to end up being 0.3 meters. So make sure you always convert centimeters to meters first. Okay, so we know our range here is 0.3 meters. And we do not yet know how long the ball is in the air for either. So then looking vertically we know our acceleration is always going to be that negative 9.8. Okay. We know that our ball traveled a vertical distance of negative 95 centimeters because it ended 95 centimeters or 0.95 meters below where it started. And then since it was rolling horizontally as it went off the table, that initial y velocity is again going to be 0 because the ball initially was not moving up or down at all. Okay. And then we still don't know how long that ball is in the air for. Okay. So our end goal is to find our initial x velocity. Okay. And to find that, we're going to want to use that range equation. That our range, or our horizontal displacement, is equal to our horizontal velocity times time. Okay. So we know that horizontal displacement is 0.3, but we don't know either of those variables yet. So before we're able to solve for that horizontal velocity, we need to find how long that ball is in the air for. And we're going to find that time by looking vertically first. So again, we know more information in that vertical direction. So we're going to start off by looking vertically on that y. Okay. So we're going to use that same equation where we have our displacement, 0.95, equal to our initial y velocity, or 0, times time, 1/2 times our acceleration, which we know is negative 9.8 c squared. Since we only have one unknown, that time, we can use algebra to find that that ball is going to be in the air for 0.44 seconds. Okay. So now it takes 0.44 seconds for the ball to hit the ground. So we want to see if it was able to travel 0.3 meters in 0.44 seconds, how fast was that ball moving horizontally? So looking back at our range equation, we have our 0.3, our horizontal displacement, equal to that horizontal velocity, which we're trying to find, times how long the ball is in the air, that 0.4. Okay. So to get that velocity by itself, we divide each side by 0.44, and we find that the ball was going initially at a rate of 0.681 meters per second in the horizontal direction. And again, since we have no acceleration, no forces acting horizontally, we maintain that same initial horizontal velocity the entire time. Okay. So that is all we have for you guys today. If you have any questions, let us know. Main ideas again, remember your only force acting on an object in the air is gravity. So we're only going to have acceleration when looking at the y direction. Whereas horizontally, those velocities are going to remain constant. And that's kind of why we're going to look at those horizontal and vertical directions separately. Okay, because we only have forces acting in that vertical direction. Okay. So I hope you guys have a great day. Let us know if you have any questions as you're working on your homework.